He's a co-founder and CEO of OmniML. It's an early-stage startup focusing on delivering efficient AI for edge devices. He has extensive industry experience in hardware acceleration and ML systems. Previously, he's worked at Facebook AI, Falcon Computing Solutions, and he has great experience and expertise in acceleration and optimization of neural network inference. And he got his PhD from UCLA.
Thank you. Thank you for the introduction.
Okay.
All right. Good morning, everybody. Thanks for joining the tinyML Summit. Very excited to be here, meeting all of you in person. It's been quite a while. And my name is Steve Wu. And in today's talk, I'm giving an introduction on behalf of Professor Song Han, assistant professor at MIT ECS, Han Lab, mainly focusing on the recent research that came out of Han Lab. How are we dealing with the emerging problems, our emerging issues, and then the advancement in tiny vision? And Song and I started this venture, OmniML. We co-founded it last May. And I will leave a little bit of time by the end of the talk and tell you more about it. So as you know, that one of the biggest problem for tinyML is a lot of the additional hardware constraints. For example, the memory, right? If you're looking at the cloud AI, which is running on teraflops, capable GPU with 32 gigabytes of memory, all the way to microcontrollers, which only have hundreds of kilobytes of memory. That's a whopping 100,000x smaller in terms of the memory capacity. And that really illustrated the fundamental problem in tinyML. The difficulty is all these additional hardware constraints where AI in the previous decades of evolvement have basically been without any constraints, right? So now how do we bring this mismatch of all these additional constraints back to the fundamental algorithm of AI? And that is the crux of the problem that we need to solve for tinyML. So just to give you a highlights, in the past 3 years, we have at Han Lab at MIT, we've accumulated many generations of technology that, as a result, made it possible for us to run real-world, complex vision tasks on really tiny microcontrollers like these, right? So this is STM OpenMV with hundreds of kilobytes of memory, megabytes of flash, running a couple hundred megahertz of CPU. Yet, as you can see, we're running real-world vision tasks like face mask detection, running person detection at almost real time with a good reliability. So there's a great journey that took us, making all these complex applications working on small devices like that. And I think that's what we want to highlight today. How is that journey? How are we making that possible? So just to give you a little bit, a brief look at the history of these, what we call the MCUNets. At the starting point, the baseline is MCUNet-v2, right? We take MCUNet-v2, of course, we need to shrink it aggressively to make it fit on such a tiny devices. And then in 2019, we have a work called proxyless NAS, basically explore the design space of MCUNet-v2 and then give a couple of points, higher accuracy, smaller model, and then we can fit more model onto this tiny microcontrollers. And then in 2020, we came out of MCUNet, so that's the first generation of MCUNet. And then in 2021, we came out of MCUNet-v2, so that's the second generation. From proxyless NAS, from 2019 to 2020, we reduced the size or the memory consumption of that model by 3x with increasing accuracy on these visual wake words applications. So this is detecting whether a person is in the scene. And also we have this entire front curve where we increase the maximum accuracy to about 92%. And then in MCUNet-v2, the milestone is we further reduce the model size by 4x, the model memory consumption by 4x. And then push this entire frontier curve. Now we achieve 94% accuracy on this microcontroller. And this is without any change in the hardware, right? This is purely on the algorithm, on the fundamental algorithm of this model. And then we're capable of delivering 90% accuracy with only 30 kilobytes of memory consumption. So big takeaway, I think that illustrates or that shows the entire community what is possible. And also, more importantly, we actually, we shows that there's a huge opportunity in the fundamental algorithm of ML itself by considering all these different hardware constraints, right? So we're without changing the hardware, we're reducing the model size by 3.5x every 12 months. We're essentially faster than Moore's law. So that just shows how much potential there is in the fundamental algorithm. And another important observation that I would like to draw your attention to is that improving the model efficiency not only means faster and smaller model, it actually means more accurate model as well. Because with all these efficiency gain, we essentially opened up more design space for this model where we can put a much better model. So take an example for MCUNet. We demonstrated that on that tiny microcontroller, we can increase ImageNet top 1% accuracy by a whopping 17%. Just show that what's the possibility of this technology unlock, right? It's being able to run all these complex vision tasks on smaller microcontrollers. So with that, I think one of the critical point that we're trying to make today is that I think tinyML is all about improving the full stack, all about improving the fundamental ML algorithm, focusing on all these hardware constraints, the memory, the capacity, the compute power. And there's great opportunity in that full stack, from design to deployment, from computation to data. So that's where I want to focus today's talk too. Talking about a few of the highlight research works in the recent years coming out of HandLab at MIT, looking at this optimization across the stack, across the entire workflow of machine learning model development cycle. So now we start with MCUNet. I think one of the key point, one of the important takeaway from MCUNet is this positive feedback loop, or this co-optimization of the model as well as the inference engine. So we get better model fitting onto the hardware, and we also improve the model inferencing, right? We have a lot of techniques optimizing the inferencing engine. For example, we have graph optimization, we have memory reuse, reduce the entire memory footprint of that model. We have different scheduling algorithms, and then we lower the precision, and then we actually do use code generation to minimize the cost of the runtime. With all of that, the important thing is that all of that innovation, all of that advancement on the engine part essentially unlocks a larger space for us to optimize the model. So that's where neural architecture search came into play. With all these new possibilities unlocked by the inference engine optimization, we now can get a much better model, right? We get a much better model, we do neural architecture search, and then, so overall, you can see this positive feedback loop between the model architecture design, between the model training, as well as the downstream optimization. I think that's really an essential point for MCUNet. And after MCUNet, right after we got this ImageNet real-world application working on the microcontroller, now we start looking at that optimized model, and then we look at what's next, right? What's the next problem? What's the next optimization possibilities? So that's where we find out this new problem where there's essentially a big imbalance of the memory distribution across CNNs, right? And then also on tiny microcontrollers, memory is the biggest bottleneck for deploying a model, right? The activation memory, the maximum peak memory consumption of a model. So as you take a look at the profiling of this MCUNet-v2 network, the first 5 layers actually becomes the bottleneck, right? The peak memory of that first 5 layers is about 8x more than the peak memory of the rest of the layers. So that's where we see the opportunity. We should focus on optimizing that memory consumption of the first 5 layers so that we'd be able to fit a much better model. So then that's where we came up with this idea, solving this imbalance memory consumption. We call it patch-based inferencing. Essentially, I won't go into too much details. Essentially, it's the idea of using tiling, localizing the computation such that you don't need to load the entire layer into the memory all at once. So with that, you can see we drastically reduce the memory footprint of the first 5 layers and keep the later layers the same. Now, this entire model, the same model, fits onto the microcontroller with a peak memory of 256 kilobytes of memory. And coming back, if you remember that positive feedback loop we talked about in MCUNets, this is not the stopping point, right? So now with these, it actually unlocks more potentials. Now, by reducing that peak memory, we're able to fit different models. We're able to fit newer models on this device. And that's where we started doing neural architecture search. We started exploring the design space to see if once we resolve this peak memory consumption problem, can we come up with a better model? And then that came the second idea is redistributing the network. So basically, when we do that patch-based inference, we essentially trade off the memory consumption with more computation. So there's slightly higher computation overhead, and to compensate that, we can actually redistribute the neural architecture, put more emphasis on the later stage of the model, and then reduce the overall computation for the first few models. And then we compensate those computation overhead away with neural architecture search and with more training techniques. So we came back to this picture, right? It's a joint automated search, a joint optimization between the inference, between the hardware and the model design. So, as you can see, neural architecture search is actually an essential part in the center point of hardware-aware model optimization. Or how are we getting different models? How are we getting better models for different kinds of hardware, for different kinds of hardware constraints? So that's where I want to introduce this work called Once for All, which many of you may already heard. It came out of Song's lab in 2020, and Song also talked about that in the tinyML summit last year. So the essential idea is that in order to explore all this vast design space of neural architecture, which traditionally is actually very, very computationally intensive, right? It belongs to a data center, right? You need a massive GPU, you need massive compute power to be able to train all these different networks for different hardware. So what we realized is that, or the idea that we came up with is essentially we train a super network that contains the entire design space. The entire design space that can then be sampled for different types of hardware, whether it's high power for GPU, or it's like a mobile phone chip, or it's the tiny microcontrollers. By including the entire design space in the training loop, and then decouple that training with the neural architecture search, we essentially unlock a great potential for hardware aware. Right? Now we only need to train the network once, and then we can customize that network for all different kinds of hardware later. So this is a great example, right? So what that unlocks is being able to explore this entire design space of the neural architectures within reasonable time, right? So compare with existing work that takes 42,000 GPU hours, we can do the same thing with only 200 GPU hours, and that also allows a seamlessly exploration of different latency for different hardware. Say I want to get a model working on this Qualcomm device for 20 milliseconds, right? The algorithm will search for optimal neural architecture for that, given that constraint. Now, if I want a model runs like 100 milliseconds on those tiny microcontrollers, the algorithm will come up with a different network architecture. So that really unlocks the potential of co-optimizing the model algorithm with the hardware. So now that we talked about neural architecture search, I want to focus a little bit more into the training, especially training for tiny models. So as you know, that in our line of research, we actually realize there is a problem with a lot of the existing training techniques for tiny models. For example, like techniques like mix-up, auto-augment, and draw block. So these techniques have been demonstrated to work really, really well for large network, such as ResNet-50, has a giga flops or giga max of computation. However, for tiny models like MCUNet-v2, these techniques actually doesn't work very well. One of the reasons is that for small models, it really doesn't have that capacity to handle all that augmentation of the data. So what we came up with in this paper, which is going to appear in iClear 2022 this year, is that instead of augmenting the data, right, we should augment the model while training tiny models. So that's where the basic idea of NetAug came into place. In the normal training loop, right, when we're training a small model, we actually permutate or augment that small network into a larger network. And then we have this auxiliary path of the gradient. And with this training in a weight-sharing fashion, we essentially augment that model during training, augment that small model during training such that we can put more capabilities into the model itself. And this augmentation only happens at training time. Once the model is trained, it is still the original model, so it has zero inference overhead, right? It's still the small model. But we've demonstrated that by applying this NetAug technique, we can actually achieve a much better results into the training accuracy compared with all these existing works. So that just to give you a highlight of that new technology we came up with. And then, if you want to learn more, please refer to our papers, NetAug, for more details. And, when we talk about trainings, the next frontier of the opportunity is actually on-device training, on-device transfer learning. Can we actually put the training happen on the device itself without the connection to the GPU or the cloud servers? So that's where we start looking at what's the bottleneck for training on device, and not surprisingly, it's memory again, right? So training in the loop consumes much higher memory than inferencing. So that's one of the biggest bottlenecks for training on device. And more importantly, we've realized that not only is training consume a lot of memory, it's actually the peak memory that is a bottleneck. For example, comparing a ResNet-50 with a MCUNet-v2, the model size of MCUNet-v2 is 4.3x smaller. However, the activation memory during training is only 1.1x smaller. So that means that even though the model is smaller, we're still taking up a lot of memory if we want to enable training. So that's where tinyML, the technique of tinyML came into place. The gist or the high-level idea of that is that instead of train the entire model, since we're doing transfer learning, we're doing fine-tuning, we're doing maintenance of the model, we focus on a selection of the model layers like the bias and other parts without that huge of a memory consumption. And because we unlock that capability, with a similar accuracy or with a similar level of accuracy, we can drastically reduce the memory footprint of that training cycle. So this work is published in NeurIPS 2020. If you would like to learn more, TinyTL, you can find out more information there. And with talking about training, let's take our attention in the beginning of this pipeline, data collection, right? So while this hardware capacity being the constraints, actually for a lot of tinyML applications, for a lot of edge AI applications, the data is another very important constraint. There's lots of cases where we do not have access to abundant data, right? The data is limited for privacy, for specificity, for domain specificity, and for all different concerns. So that's where I think another huge opportunity lies in for the entire tinyML capacity community. How are we looking at training with very limited data? And here, I just want to highlight one of our work called Differentiable Augmentation. And with that, we're able to train, again, a network with only 100 with 100 images, and enable smooth transition, enable photorealistic results. Essentially, the idea for that work is that during the training of that GAN model, we augment both the real image as well as the generated image, and then we have that co-optimization, and that really improves the efficiency of the training, and then allow us to match the original baseline's training performance with only 20% of the training data. Talking about new opportunities for tinyML, another really big opportunity I want to highlight in this talk is beyond 2D vision into 3D point cloud. As you know, there's a lot of emerging applications on the edge, AR, VR, self-driving cars that relies on 3D data, 3D voxel data, right? LIDAR data, radar data, imaging radar data. And although the hardware is not tiny anymore, but the fundamental problem is the same. The algorithm is very complex. The algorithm was designed for complex, high-power data centers for high-power GPUs. How are we making them work on smaller devices? How are we taking consideration of all the different constraints, right? So the problem is actually the same, right? So I think a lot of the techniques, a lot of the innovations that we have in the tinyML community can actually be applied to this new frontier of the research. I won't go into too much details, but I do like to highlight multiple pieces of work from MIT, from Song's lab, focusing on improving the efficiency, focusing on dealing with the constraint for LIDAR, for point cloud models. So the first is on the algorithm, right? We came up with new design primitives. We call it point voxel. That was published in Europe in 2019. Essentially, that is a design primitive focused for LIDAR models, focused on 3D point cloud models. And then with the new design space, with the new design primitive, we have new neural architecture search approach. So that's where this work, SPVNAS, published the ECCV at 2020, solving this neural architecture search under this new paradigm. With neural architecture search, remember our joint optimization of the model and the inference engine, we have a work that optimizes inferencing on GPUs, optimizing the inferencing for sparse point cloud models on GPU. That's the work torch bars, which is to appear in MLSys this year. And we even go beyond that, right? From the inference engine, we go all the way to the hardware layer. We actually propose a new architecture focusing on improving model inferencing for point cloud. So that's the point ACC work published in Micro last year. Given the interest of the time, I won't go into too much details about all these works. But I think that the takeaway is that there's really a huge potential. There's a huge opportunity for tinyML to look at all these new frontiers. So for a takeaway, right? Let's come back to MCUNet. Come back to these positive feedback loop between the model design and then the hardware that keep coming up, become the repetitive theme in this picture. New technology or new improvement on the inference engine side unlocks new potential for algorithm. And then the potential of the algorithm, and together with these positive feedback loop, that's where we start putting all these complex ML tasks onto reality, enable real-world AI with constrained hardwares. And one of the key takeaway is that once the model is trained, we're already limited, right? There's actually a huge space for the fundamental model algorithm itself that we can improve by taking consideration of all these additional hardware constraints. So with that, I'd like to introduce you to OmniML, which is a startup company Song and I and a few others co-founded in May last year, that is focusing on unlocking this potential in the fundamental ML algorithm by taking consideration of the hardware constraint. the key problems, right, like we talked about, is this mismatch between the model and the hardware. Today, the model are not designed for constrained hardwares. So that makes everything difficult. That makes the developer's experience very, very problematic because, designing new models with all these hardware constraints is not very natural to ML developers, right? They don't understand how the hardware architecture works, how these different level of optimization take into place. So that really leads to this, repetitive manual iterations between the model design and deployment, right? We have to do a lot of trial and errors because, ML engineers don't know how to optimize the model for the hardware. That calls slow adoption, which leads to less revenue, less volume. Right? It's a big problem in this industry. And at OmniML, we focus on making the model fit from the beginning, before the model is trained. Make the model inherently hardware aware, inherently fit on the hardware. So, start from the beginning, start from the model design phase, and all the way down the pipeline, focusing on the full stack optimization opportunity. So that's where unlocks potential for us to really optimize any vision task on any hardware. For example, CV for mobiles, like a real-time post estimation on the Qualcomm mobile chip, or even 3D sensor fusion, right? 3D detection on the embedded NVIDIA system, fusing 6 cameras together, running the detection at real time, and also smarter cameras, right? Leveraging the potential of the existing camera hardware, putting smarter, more complex AI algorithms onto the camera itself, allow everything to happen locally rather than coming back and forth from the cloud. And finally, all the way to microcontrollers, unlock possibility of running computer vision on microcontrollers, right? For remote places, for factories, unlocking a real significant real-world applications, many unimaginable applications with tinyML. And we've already made a lot of tractions ever since less than a year of in business. And also, I'm very happy to announce that we're coming out of stealth mode today. We're actually doing a company launch at this event with media coverage. So come check us out later on. So. Our founding team were expert in efficient deep learning with Song, with a team behind all these great research at the driver's seat. And with that, concludes my talk. Thank you very much. Come talk to me if you want to learn more.
On now? Yeah, okay. Thank you very much, Dee, for this very interesting talk. We have 5 minutes for questions, if anybody's got any. In the meanwhile, actually, I wanted to ask while we're waiting for this MCUNet that you were talking about, do you guys have any, how much of it is based on doing the architecture search and how much of it is something that even without architecture search you could start using today?
Yeah. Actually, that is a great question. I think if you, in the paper, there's actually an interesting graph. Basically, architecture search only, inference engine only, and then architecture search together with the inference engine. But the takeaway is that, architecture search only improves the final accuracy of the model by a couple of %. And then if you're doing inference only, it also improves the model by a couple of %. But if you put them all together, that unlocks the maximized potential, right? That gives you the highest accuracy. So I think that's one of the key ideas of the MCUNet is this combination, because any new architecture or any architecture is actually coupled with all these inference engine, right? So for different inference engine or different compiler optimization, we actually can design a better model. We can design a different model for that.
Okay, so MCUNet is not one specific style, one particular model, it's kind of a family that you can generate.
Exactly,
okay.
Exactly, right, yeah.
Great.
Hi, very interesting talk. I saw you mostly presenting papers. I was wondering how do you, in the future, connect that to like real product and what's the plan about that? Thanks.
Thank you. thank you very much for that question. I think I will. We can catch up offline about the new opportunities for OmniML, but I think the research, the fundamental research, is very important to show us like essentially what's possible, right? MCUNet, I think that's a flagship that show the world it is possible running even on these tiny microcontrollers. That really unlocks. It's like the 4-minute mile, right? So it shows that this is possible. But in production, in the industry, we really have to look at the exact pain points of the customers, what their problems, like I talked about a little bit earlier, is this long design cycle, right? Because designing model with hardware awareness is unnatural for ML, for the existing ML community. So that's where the company is focusing on. Really unlocks or bridge the gap, and then creating a software tool that helps taking all these hardware feedbacks into the design cycle, help all these ML developers come up with better models. I think that's, on the high level. I can go into a lot of details about how we're commercializing that. Happy to catch up with you later on. Yeah.
Thank you so much for this interesting talk. I have a question about the neural architecture search, especially when you add the hardware-aware component. Neural architecture search is like costly. And when you add the hardware-aware, for different hardwares, that even increases the search space significantly. How do you address this, in your approaches to make the hardware, the NAS piece, efficient?
Yeah, that's actually a great question, and I think that's the fundamental motivation for us for the once-for-all network, for the once-for-all work. Essentially, instead of doing the neural architecture search for model, for hardware, right? We decouple that, the overall loop. Now, we're not doing the search for every hardware. Rather, we first abstract the entire design space into a super network, into a larger network. That super network can then be sampled for different hardware. Just give an example, right? Instead of training, let's say, a 3x3 convolution kernel, we're training 1x1, 3x3, 5x5, 7x7, all at the same time. And then after that is trained, we have a path to then customize that model, without retraining the model for different hardware. Now, with the GPU, we may, prioritize those large convolution kernels. For smaller microcontrollers, we may, using smaller, layers. So that's the overall idea behind that work is decoupling the training and then this customization. So I think that's the fundamental idea behind once for all. Yeah, to solve that problem.
Thanks.
Okay, thank you very much.
Okay. Thanks, everyone. Yeah.
And we are very thankful for our sponsors. The premier sponsor this year is Edge Impulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Sentient. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. Gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support and, more importantly, for them being part of this community and driving it forward.